Welcome everyone. In this video I'm going to show you a nice little AD converter. So it is this circuit right here, and the interesting part is this board here. This is a CS1237 24-bit AD converter, and why it is interesting is because it's a very cheap module and also very cheap AD converter, but it's quite powerful. So as I said, it's 24-bit resolution. It has a built-in PGA, which can go up to 128, and it also has quite a nice sampling rate. So it is 1280. So this chip, or actually this board, can be a very good alternative for the HX711 board, which is also a 24-bit AD converter used for load cells, but it is much slower. So this might be a better choice. So here we can see that we have another chip next to the AD converter chip, which is this here. So the other chip here is actually a voltage reference chip, and it has two purposes. Despite the fact that this AD converter has a built-in reference, which is 2.5 volts, we don't use that, but we use this voltage reference right here, which also happens to be 2.5 volts. But it is not only feeding the reference input of this board, but it is also feeding one of the pins here. And this is because it can be used in a ratiometric measurement. So both the reference and the device in use or device in test is receiving the same reference voltage. And also, if there is a disturbance in the reference voltage, then both the AD converter chip and the connected device feels the same, so that kind of noise is cancelled out. So then we have A plus and A minus pins, which are the positive and negative inputs for this ADC chip, because it has a differential input. So actually the range provided by this 2.5 volt voltage reference is split into half. So when not using the PGA, so PGA equals 1, the range of this AD converter becomes plus minus 1.5 volts. So we can measure negative signals as well. And of course the AG and E is the analog ground. So when we have these kind of 4 inputs, we can use it with load cells. But in this simple demonstration, you can see that I just have a simple 10 kilo ohm potentiometer. And then the device that will drive this is a simple Raspberry Pi 2040 board. This is a Waveshare board. And you can see that it has a nice USB-C port, and it has a very tiny form factor. This is a small breadboard. I don't have a banana for scale, but I can show you. I can show that this board is quite tiny. So you can see that the board is barely 3 centimeters long. So it's really small. And you can see that there is only 2 wires go from the microcontroller to the AD converter, because you can see here that there is only a D out and an SCK pin here. And why is that? Is because this has a bidirectional pin, which is the D out or data ready, so we can both read and write this pin, and we have the SCK, which is the clock pin. And by using only these 2 pins, we are perfectly able to communicate with this AD converter. And I developed the code for this from scratch, so I will explain you how this thing works. And then in future videos, I will show you some nice applications, for example, load cells and other cool stuff that can be used or utilized with this AD converter. And before showing the code, let me go back to this circuit board here. So I earlier said this AD chip has an internal reference voltage, but we are feeding it with an external one. So actually you can modify the config register of this AD board, and it can use its own internal reference. But it is actually internally separated, so there is nothing to switch, let's say, inside the chip package that can, let's say, route the internal reference voltage towards the input of the reference voltage pin. But we have to do that manually. And that is done in the following way. So right here, pin number 1 is the reference voltage pin. If you look carefully, you can see that that goes up to the pin here on the reference pin, on the reference voltage source. But then that can be also connected by this R5 part, which is then pin number 8, because that is the VREF out of the AD chip. So what we can do is that if we don't have an external AD, or if we don't have an external voltage source, reference voltage source, we can short this part here, so the R5 resistor, either by using a 0 ohm resistor like it is done here at R2, or we can just simply put a big solder blob here and then it's done. And then that we make sure that the AD converter uses its own voltage reference, which is the internal voltage reference. And just for fun, let's plug this thing in and let me do a quick measurement, but of course it's nice if you see also. So I'm just trying to show you the reference voltage value. So this goes here and this goes here. And of course I'm blocking it. So 2.495 volts is the voltage reference. That can be also checked on pin number 1 here. And then since I disabled the reference, then I cannot measure anything on the other pin. So that is disabled right now. And then of course this is the digital voltage, 3.3 volts once I can get the contact. And then there's nothing else that I can measure because the rest is just ground and stuff. So then we could see that the reference voltage is also relatively precise. So now let's move to my computer and let me show you how the code works on this microcontroller that drives this AD converter and reads its values. Alright, so we are in front of the computer and let's go through the code to understand how it works. So in the beginning, I would like to show you this small macro that I kind of defined here. So if you look at the datasheet, you will see that the operations or some of the operations require a delay which is below 1 microseconds. Namely, it's 455 nanoseconds. And that is not really possible by using the regular Arduino framework, because the smallest amount of delay that you can use is 1 microseconds, but this is half of it basically. So what we can do here is that essentially we can run, let's say, empty cycles of the CPU or MCU in this case. And how it is done is that we have this line here where we have this NOP, which is no operation or something like that. And in the parentheses here, I actually have 11 of that. And that is 11 times the time which takes for the microcontroller to do 1 cycle. Now in this demonstration, as you could see, I use a Raspberry 2040 0, which has 133 megahertz clock cycle. So I wrote down the formula here. So 1 clock cycle is 7.52 nanoseconds, and then this is somewhat experimental value that I came up with. So in this part of the macro, I have 11 of this NOP, which makes 82.72 nanoseconds of delay. And then in this function, I call this macro 10 times. So actually this is not 455 nanoseconds, but it is more like 827.2 nanoseconds. But after playing around with the microcontroller and the AD converter, this is what I figured out to be good enough. You will see the code, you can check it on my GitHub, so you will see the additional comments if you want, but I scroll downwards now and show you the rest of the code. So as I told you, this chip has a kind of a simplified SPI. So we have a clock pin, which I defined to be the 0 pin, and we have a D out or data ready pin, which I defined as the pin number 1. And as I wrote it here, you have to be careful with certain microcontrollers, because the pin 0 and pin 1 is usually assigned to, for example, the serial communication, especially with Arduino Uno or Nano. But in this case I could use this, but actually you can use any GPIO pins as long as you don't want to use them for another purpose. But for these two Arduinos, you have to be a bit more careful, because if you use pin number 0 and pin number 1 on the microcontroller, you won't be able to use the USB, so be careful. And then I just have two variables. One is the ADC reading. It's a 24-bit AD converter, and the long gives us 32 bits, if I'm not wrong. So we can store the 24-bit in the 32-bit variable. So it's the correct choice of type. An int would be overflowed with the ADC reading. And then the PGA divider here is 1. Actually, I could use this 1.0. Sometimes people like to define the floating point with the decimal point just to further indicate that it's a floating point. And why I use an integer here still as a float, because it's just more convenient for me to see that this will actually be used as a divider for a floating point number. So it's just extra convenience, but yeah, it doesn't matter. So then in the setup, we start the serial communication. This is the USB communication, and then I just wait for the serial until it's available, and after it became available I just wait 3 more seconds, because that allows me to have an extra time to click to the top right corner and actually open the terminal. So when I open the terminal, I will see this welcome message. So then this moment we have 2 pins. So the D out, that is an input pin, and I pull it to low. I know that it doesn't make sense, or doesn't suggest too much sense for an input to write a value to it, but trust me, it works as I want it to. And then we have an output here, which is also pulled to low. This is just to follow the guidelines based in the datasheet. And then we make sure that the chip is awake, so that is done in these 2 lines. So basically we are waiting until this condition is true, and then after this condition is true, then we wait until this condition is true, because in the datasheet you can see a graph which shows how the chip wakes up. And then I wait 1 second just to be sure that the chip is ready. And then I set all the 4 parameters in the config register according to my own arbitrary choice. So the input, there is only 1 input, but it can be assigned with different values. I choose CH0, which is the regular input where we really measure the voltage. And PGA is 1, so basically it's the default setting, so we can use the full scale of the input. And then the data rate is 10 Hz. This is also the default, the lowest possible sampling rate. And then I disable the internal voltage reference. And then that's all. So now we can further proceed. And first I show you how a acquisition is done, because when we want to read and write a register, it is based on this function. It starts from this operation. So this is a function which I wrote, and it will return with a long, because it will return with the raw 24-bit conversion value from the AD converter. So we wait until the data ready falls low, and how we do that is that we have an empty while loop here, which stays in the loop until this is true. So until the data, or as long as the data ready pin or the out pin is 1, we are just running this empty cycle. And then data ready was low, so then we can proceed further. So internally I just have a value which I call result. We store the 24-bit data in this variable. And then we wait 1 microsecond after basically the data ready went low, and this is equivalent or roughly equivalent to the T4 timing on the timing chart. And then we can start shifting out the data. And that is actually very simple because we can manually shift it out. So we don't need to mess around with the SPI and its clock and whatever. So here we basically manually toggle the SCLK pin. So set it to high and low with a certain time period. And while we do this toggling, we shift out the bits starting from the MSB, most significant bit, and then we just keep putting the incoming bits into the result variable. So here we have this result, and then we have this vertical line, which is the logical OR operation. And then what we do is that with each clock cycle, so we set it to high and then wait, and then we read the status or read the value of the out pin, and then that reading, which can be either 0 or 1, is shifted up to its corresponding place, which is 23 minus I. So in the first iteration of this for loop, this is 0, so then the bit here is shifted to the left to the 23rd bit in this result variable. And then we finish the clock by pulling the SCLK low and wait again. And then in the next iteration, the I will be 1. So now the next bit, which is bit number 22, that is shifted up and combined together with the result variable, and so on and so on. And in the last iteration, when the for loop is at the 23rd iteration, then the parenthesis becomes 0, so we don't shift basically. So the last bit, the LSB, least significant bit, is just combined together with the result value, which already contains 23 bits. And then the 24th bit, the last bit, which comes in the last iteration of the for loop, is just simply combined together. And then it's done. And then if we continue looking at the timing chart, we see that there are 3 more pulses which we have to do. And that is pulse number 25, 26, and 27. And there we just simply toggle the clock pin with the corresponding clock or pulse cycles. And then we are done. And after this is done, we just return with the result, which is the conversion result. And that can be just displayed on the serial terminal. So now we want to see how to get the value of a register. So we define a byte variable here. 1 byte is 8 bits, and the register holds 8 bits, so this is perfect. So here I perform an ADC reading. As I said previously, this will be necessary. And actually, I could only just call this function. I would not need to store this in a variable. Actually, you could get rid of this variable totally. But for example, if you want to reuse the reading even when you read a register, then you can just refer to this variable. And then the datasheet says that after reading out the ADC, after the 27th pulse, we have to set the D out to output. This was input previously because it was reading the output of the ADC chip. But now it will be an output because it will send the data to the ADC chip. So the shifting from input to output is done. Then we emit 2 clock pulses. So we advance with our progress. And then we have to make 7 more pulses. So clock pulse number 30 to 36. And what this does is that it sends out a reading command, which is this 0x56 number. And that is basically with each clock pulse, it is shifted out by writing the corresponding bit on the D out pin. So this is how it's done. And after we shifted out the command, we send one more pulse here. I know the for loop is totally unnecessary for one single pulse, but I copy pasted all these kind of clock generation thingies, so I just felt a bit lazy to clean this up. But yeah, one more pulse is shifted after we sent the read command. So now we send the read command to the ADC chip, and then the ADC chip will respond. So what we have to do is that we have to set back the D out pin into an input pin, because it will receive data. So then I set the register value to 0, just because previously it could have been something else, or whatever. Maybe the value could have been compromised by some way. I might be paranoid, but yeah, let's set it to 0 before we fill it up with data. So then what we do here is that we just run 8 pulses because of the 8 bits that we are going to read out. And similarly to the strategy that we used to read out 24 bits, we shift out only 8 bits. So we pulse the clock, so clock goes high, wait a bit, and then we read the status on the D out pin, and then place the MSB to its MSB place. So in the first iteration, I is 0, so then this becomes 7. So the value that we read here, either 0 or 1, is shifted up to the bit number 7. And then this is repeated until I becomes 7. So then this becomes 0, and that is when the LSB comes in. So the value of this is just simply combined with the register value, but there is no shifting done because the bit 0 will be put to its place. And after this is done, we send out just one more pulse, and then that's all. I just set the pin to input once again, just to be sure that everything is done, and we are ready to return with the register value, which is an 8-bit number or a byte, and that can be displayed on the serial terminal later on. And then we have to know how to set a register. So I wrote a function which receives 2 arguments. One is the register to write, and in this sense actually we have the same register all the time. So we are not choosing a register here. It's just poor choice of name from my side. This is the parameter to write. And then this is the value to write. So we update one of the parameters, for example, sampling speed, and then this will be the value which will tell which sampling speed to choose. So here I just summarized the datasheet for myself and for you, whoever uses this code, so we can skip this. And then what I have here is that first I read the register. So I just store the register value, which is the most recent register value. I want to see how it works and what was the most recent setting. So I do this. And then I also define a so-called byte mask. And that is declared as totally 0. And I will show you and tell you why I do this. So based on this argument here, I made a big switch case statement here. So if the case is 0, then I want to modify the input channels. So what that means is that first I create a byte mask here manually, and I will use this as this. So how my byte mask will work is the following. As you can see, these are all 1s, and these 2, which correspond to the channel input selection, are 0. So you see in the next line that the register value will be the register value and the byte mask. So this will actually make sure that since I use the logical AND operation, then whichever bits in the register value are in these two places, they will be erased. Because when you use the logical AND operation, then both let's say bytes have to have ones at the same place to make their result to 1 as well. So since the masking byte is 0 at the two places where we have the bits to select an input channel, then this operation will erase those bits, whatever they were. And why I do this is because I want to update them later on. So then we have another deeper switch case statement, and this accepts the value to write as the argument, let's say. So then if that value is 0, that means that we have the first option in the table where we can select inputs. So what we have here is that this will be the channel A, so we are using the proper voltage input channels on the board, and that is actually done with this command. So we read the 0th or first in this case, but we start numbering from 0, 0th parameter and its 0th possible option. And what we do is that the register value will become this. So we combine the previously masked register value using the logical OR operation with this operator. So we keep everything as is, and then we print to the serial port that the channel is 0. This is just for the user to know what they did. And then case number 1, so that's the second option in the table, that is reserved. We don't really have to do anything here, so I don't do anything. So I just let the user know that this is a reserved channel, invalid option, blah blah blah. So this doesn't really matter. And then the next is when the user sends this command to the serial port. So then this is what is in the table, and this will be the temperature channel. So then we let the user know that this is the temperature channel. And then the number 3 is when we send this command to the serial terminal, and then that is when we want to have 2 1s or 1 1 at these places, and then that is when we internally short the chip, and yeah, it is what it is. So then this is done, so we can go to the next selection, which is the PGA. So then, as you can see, the masking zeros moved up 2 places towards the left, because these are the 2 bits which set the PGA. So we keep everything unchanged except these 2 bits here. How we do it is that the most recent reading of the register is logical ANDed together with the mask. So then we can work with the rest of the things. So if the PGA is the first option, then we read the first position in this, let's say, byte, and then the 0th option. So we keep everything unchanged, because in the table that is 0 0. I set the PGA divider to 1, because later on this will be relevant, and then we tell the user that they selected the PGA equals 1. And then the next PGA is when the PGA is set to 2. So that is done with this command here. And now you can see that instead of 0 0, we set 0 1 to the PGA. And then the PGA divider is 2, simply 2. And then we let the user know. And then following the same kind of logic, then here we combine again, and you can see that the 2 bits here is now 1 0, and that will be equivalent to the PGA 64. And then in the next step, when both bits are 1, so the 2 bits here are 1 1, the PGA is 128. So then that's that. And we can do the same with the D rate. I speed up a bit here, so you can see again that we have 2 bits that we can manipulate, and again we erase the most recent register value by masking these 2 bits out from it, and then we will update it according to our newest setting. So as you can see, we can have 10 Hz, so we have the W2 space 0 command. So again, the 2 bits here are 0, 0, so we keep everything as is. And then 40 Hz, 0, 1. 640 Hz, it's 1, 0. And then 1280 Hz, 1, 1. And then each time we changed it, we print it on the serial that there is a new sampling speed value here. And then here I implemented this one single bit here. So if the value to write is 0, so it's this one, then I just simply use the bit write instead of masking, because it's just one single bit and there is a function for it in the Arduino, which is very simple. So then the register value's 6th bit becomes 0, and then this means that the internal reference of the chip is enabled. Or we can send the number 1, then this is basically the default value that we should use, is that the 6th bit is, or bit number 6 is set to 1, and then VREF is off. And then if we would send another number, then I just have an empty else here, so other values won't trigger anything. So that's simple. So this part only just updated the values locally in the microcontroller. So now we have to do it with the ADC chip as well. So we do an ADC reading, similarly to the reading of a register, and then we set the D-out pin as an output, because previously it was an input because we were reading from the ADC. Again, 2 new pulses, and then we have 7 pulses, and now we send first this value to the AD converter 0x65, which is the write command. And once the write command is shifted into the AD converter's register, then we do 1 more pulse here. And then in the next 8 pulses here, we shift out from the microcontroller to the register of the AD converter our new register value. So the config register is updated. So we have the register value, which is a byte, 8 bits, and then bit by bit we shift it into the corresponding register. And after that is done, we do 1 more shift, or 1 more pulse, if you like, and set the D out as an input, and that's done. So now we know how to read data, how to acquire data, how to read register, and how to write register. So let's put this into a working system. So I wrote a very simple loop here. We wait for the serial, and then we are looking for a character sent from the serial port. And then based on that character, using this switch case statement, we can do different things. So if we send a capital R, then we read the register. So we simply run the get register function and put the value of it into this reg values byte. And then first I just print this, and then I add the rest of the values to this line by shifting out or printing out the 8 bits one by one to the serial port. So then we will see 1s and 0s, but it will be very easy to read because it is very easy to cross-check with the settings in the datasheet. Then if we send a capital A, that will be a continuous reading. So what I do is that here is a while loop, and while we don't send a small s to the serial terminal, S stands for stop, then we acquire data. And how it's done is that first we acquire the data, then we check the sign of it, And based on the bit number 23, which is the sign bit, we can decide if we should or should not mirror the data. Because if this becomes 1, so we can enter the if condition here, then the ADC value that we recently read has to be basically mirrored around the 0. And this is how it's done. So this is how you represent it as a negative number. And then what I do below here is that we have this voltage value, which is 1250 divided by the PGA divider. So first of all, the 1250 comes from the formula in the datasheet, because this is 0.5 times the voltage reference. The voltage reference is 2.5 volts, but I want to represent the data in millivolts, so 2500 millivolts, and half of it is 1250. And you could ask, why half? Because the full range of the AD converter is divided into two. You have the negative range and the positive range. So then that 2.5 volt, which is basically described or defined by the reference voltage, is split into half. So the full range is between this half of the 2.5 volts, basically. And then we need to divide by the gain, or PGA. And then this is multiplied by the LSB, basically, least significant bit, and that is then divided by this number, which is simply this number, which corresponds to the range of the AD converter. And then once this thing is done, I just print the raw value, and I print the voltage value with, not 8 but 10 digits. And then how we write the register, as you could see, we have to send basically 3 characters, 1 letter and 2 numbers. So first we parse obviously the W, so we already parsed it in the beginning of this switch case. And then after the code detected that we received the W, it comes to this part. So first we parse the first number, which comes after the W, and that will select the parameter in the register. And then we have to parse the next number, which is after the space, and that will be the value that has to be updated in the register. So then those 2 numbers are parsed, so then we pass those 2 numbers to the register. And that's all. 400 lines of code, maybe a little less if I write a bit more efficiently, but it totally utilizes the CS1237 AD converter. So now what would be interesting is to see this in action, so I just show you a few demonstrations. So now you can see that this is why I added 3 seconds of delay, so I could catch up with the terminal and see these. And you can see that here we have different default values that I introduced you in the beginning of the code. So the channel is the default channel, PGA is 1, D rate is 10 Hz, and VREF is off. So let's do a reading of the register right now. And we can see that only this value is 1 because of this, the VREF is off, but everything is 0. So let's change the PGA just for fun. So that is on the parameter 1, and let's change it to PGA equals 2. So this is fine. And I read the register again, and we can see 0, 1 here, because that's for the PGA setting. And then let's do some similar exercise with the sampling speed. So sampling speed is 40 Hz now, and if I read the register again, then that becomes 0, 1 again here. Obviously I don't want to change the channel here because I want to measure some voltage. So then what we can do is we can do some sampling, and let's do that by pressing A. So now this is a good example, because you can see that the value is unchanged, and actually you can see that we have 625 here, which is suspiciously half of the full range that we have. And here we have this 8388607, so 8,388,607, which is again half of the full range in the in bits. So the problem here is that we are feeding a higher voltage to the ADC that it can actually measure. So let me tune this down. So now we are reading 430 millivolts, and I will try to confirm this with a multimeter. And my multimeter reads 435 millivolts, so it's close enough for me. So I think we can accept this as a valid reading. But yeah, the main thing I want to show you that this thing works, and you can see that it responds very quickly. If we want, we can stop this. I can set the sampling rate to a slower value, and I can even set the this was the PGA, so let's change the sampling rate as well, and now start the reading again. So you can see that now the incoming data is more sluggish, but for example I can go up to higher voltages, and then of course I will hit the max range here again, and now I'm below it. So now we can read, and you can see that actually where the microvolt starts, so here that digit is also not too unstable. So this is like 719 millivolts. So then here starts obviously the microvolt range, and I'm not averaging anything or not filtering everything or anything, so this could be improved. So yeah, this works. I stop this, I try this just to demonstrate. Now you can see that the terminal goes bananas because the incoming data is very fast. And then with this I think I can conclude that this is a very nice little AD converter. So if you are interested in more resources, please visit my website. I also uploaded this code to GitHub, so it's not on my Patreon, but if you feel, you can donate me either by becoming my Patreon or just leaving a donation. But I think this could help so many people that it is worth to publish it on GitHub. It's not a library, because I think it's too little code to struggle with all those things to make it into a library. But yeah, it can be used very easily. And since the datasheet of this thing is in Chinese, I hope that my translation and interpretation will help you if you want to go and dig deep with this AD converter. And obviously I will not stop with this AD converter just here. So I will show some applications with different devices connected to it, and then we will see what are the capabilities. This AD converter is supposed to be used with, for example, load cells. So I will connect it to a load cell in a future video, and then we will see what it can do. So once again, visit my website and check the link in the description. I left there all the usual links for useful resources. And I hope that this video was useful to you. I hope you learned something, and see you in the next video.